Welcome back to the Stats Primer slides. And so where we left off was how randomness is really important in statistics and the behavior. Randomness, which got us to random variables, which is how we sort of, count what's happening and describe a situation. And then we want to describe the behavior of that situation. So we used flipping a coin 10 times, and we were counting the number of heads out of the 10 flips. And we said we have an idea of how that behaves, of how that random variable behaves. So it's most likely 5, but it's not always going to be 5. Okay, and so on and so forth. 4 and 6 should be less likely than 5, but more likely than the other stuff. Then 3 and 7, then 2 and 8, then 1 and 9, then 0 and 10, probably. Okay, and so we want to describe that behavior, and how we do that is with what's called a probability distribution. Okay, so it describes all possible outcomes of a random variable. So for flipping a coin 10 times and counting the number of heads, it's 0 through 10, and it has the associated probability that each of those things are going to happen for the discrete case, and then in the continuous case, which I will mention very briefly, or we won't get too far into it. It's a little bit different. Okay, so there are lots of different probability distributions out there, but there are ones that come up commonly, and those ones get names. So there are a couple really prominent ones. The most prominent probability distribution out there is the normal distribution, or you might call it the Gaussian distribution. Okay, certain fields call it normal, certain fields call it Gaussian. Okay, after Carl Friedrich Gauss, who probably didn't come up exactly with the distribution, but made some important inroads in the distribution and thus got his name attached to it. Okay, so there's the normal Gaussian, there's binomial, there's the Poisson, or Poisson, if you don't want to use the French pronunciation. Yes, that does mean fish in French, but it is a person's name and a distribution. The chi-squared distribution, TF, there are lots of them, hundreds of them out there that are important enough to have names. Okay. They also have common functional forms. So they have names, but of course that only goes so far. It's a name, but what is underneath the name? They have functions associated with them. So the normal distribution looks like this, or rather I should say the PDF of a normal distribution. Probability density function looks like this. So it's a function where you know the mean and the standard deviation, which we'll get to in a minute, and then you plug in x and it gives you something back. Now, what that something is depends on if it's a discrete or a continuous random variable. But again, maybe I'm getting a little bit ahead of myself here. So anyway, it has a functional form. Okay, so that functional form is important, and R has almost any probability distribution that you can think of in it. So it has very good support for probability distributions. Okay, there are 4 different characteristics of a distribution that we can be interested in. So R has 4 functions for every distribution that it has in its sort of base arsenal, and then people have also made other ones. Okay, but there are 4 of them. The probability density or mass function, so you've seen me, or you've heard me, sort of distinguish between them. Okay, and all of the functions have a same form, and so these probability density or mass functions start with the letter D. And so, for instance, the normal distribution, if I was looking for the PDF of a normal distribution, I would use D norm. Okay, so the 2 underscores after D are a space for you to put the name of the distribution. It isn't going to be the full name. It'll be part of a name because, of course, the full name might be really long. So norm is for normal, and so D norm gets us the PDF. Okay, so D norm, DT, D chi square, so on and so forth. Okay, There's also a cumulative distribution function. So a probability density function gives us a density at a point. If we go too far into PDFs, we start, well, not very far in, we start getting to integrals and calculus. And so if you haven't taken calculus before, I don't want to scare you. I don't want to get in there too far into that discussion too far because, well, we might not all know calculus. So density and mass functions there. Cumulative distribution functions start with P. Now, a cumulative distribution function, I believe I talk about it in a couple of slides, but it measures probability up to a point. Okay, and we'll get there. Inverse CDFs, I need to go backwards, well, sort of inverse with Q, and then random samples from a distribution with R. So P, D, Q, and R are the four basic ones. So now let's get to a question that I might ask in an intro probability course, intro stats course, or a discrete math course or something like that. Suppose that I have a random variable x which tends to have, or which has, a normal distribution. So that n, so the tilde means has a distribution associated with it. Everything to the right of the tilde is the actual distribution. N is going to stand for normal here, so it is a normal distribution with a mean of 100, a standard deviation of 15. Normal distribution, if we conjure up some of your knowledge, looks like a bell curve. Okay, the center is the mean, so that's the first number. So the center is at 100, and then it's spread out according to the standard deviation, which is 15 here. And actually interpreting standard deviation is a little bit tougher. I want to find the probability that the random variable, like the experiment happens, and I get a value of the random variable less than 90. Okay, so let's make believe that X is someone's IQ score. Okay, I randomly select a person. What's the probability that randomly selected person is going to have an IQ of less than 90? If IQ scores are normally distributed with a mean of 100, standard deviation of 15. Okay, and so I have a lot of code here that doesn't actually answer the question, but gives you a nice plot of trying to visualize what that would look like. So the center is at 100, so the peak, it looks like a bell curve, the peak is at 100, okay? And I want to find the probability that X is less than 90. For a normal distribution, I need to find the area under the curve to the left of 90. Okay, because that's how probability is found for normal distributions and in general all continuous distributions. Again, if none of this makes sense, well, I guess you should be sort of worried because it was a prereq for this course and you've lost some stats knowledge, but it isn't going to kill you at the moment, we'll say. Okay, so anyway, I need the area under the curve to the left of 90. If you've taken calculus before, you know that if you integrate a function, you're finding the area under the curve. This is exactly what we want here, but we're not actually going to integrate anything because we have these special functions. Okay, so the solution, I'm looking for area to the left of a point. I'm looking for a cumulative probability, and so I'd use a cumulative distribution function. That's a function that starts with a p and then has the distribution next to it. So p norm, I substitute in the value I'm looking for, 90, then the mean 100, and the standard deviation 15. Okay, and so that's going to get us the answer. So it turns out there's around a 25.2% chance that happens. Okay. Now, another place where you might find this, and now we're sort of getting into inference, is finding a confidence factor for a confidence interval for a population proportion. So a confidence interval is, well, a range of values where it's plausible that that range contains the truth. Okay, so this gets into, it gets into something a little bit deeper, which is inference, and we haven't talked about that yet, but that's the main thing that a statistics class gets into, is statistical inference, and it probably talks about a confidence interval. So, for instance, I'm interested in the average price of renting an off-campus apartment in Shippensburg. I don't know what it is. There are, I guess, a finite number of places that you can rent from in Shippensburg. Okay, and so I could do my homework and find all of them, and I could ask all of them what their prices are for, say, a similar type of apartment. And then I could actually find that mean. So I could find all of the numbers, find the mean of them, and that would be the truth. That would be the actual answer. But let's make believe that there are a lot of options in Shippensburg. Now, we know that's not true. Okay, probably less options than you want, but make believe there are tons of options out there. Like thousands of options. That's not feasible, of course, for me to talk to all 1,000 people. Thousand, whatever. And so I talked to 30 of my friends. Suppose that I have 30 friends. I'm popular. I talk to 30 of them, and they each tell me their price. What I can do is generate a confidence interval, a range of plausible values, for which I think the average price could be in. So, suppose I do that. Suppose there are lots of options. I talk to 30 or 20 or 10. The number sort of does matter, but it doesn't really matter. So I talk to a number of different people. I get their estimates, and I create an interval. We'll find out how to do that. But I create an interval, and the interval says $900 to $1,100 a month. Okay, that might be totally non-feasible, or it might be so much or so little. Probably a lot for Shippensburg. Let's go like $400 to $600 a month. Okay, so $400 to $600 a month. That tells me something. So suppose I'm really interested in living off campus, but I want to see if it's feasible, and I have a $300 a month limit on what I can afford. And so if I generate that interval and I say, on average, the monthly rent of a place in Shippensburg is $400 to $600, that tells me something, and that tells me maybe it's out of my price range. Now, for that, maybe I just look for the cheapest place that I can if I really want to get off campus. But the reason for my possibly weird example is that a confidence interval gives us a range of plausible values, which we may want, and tells us something about the population, proportion, population mean, something that we're trying to think about, gain evidence about. That's the whole idea of statistical inference. Okay, and so now fast forward to the interval. So here's the interval, p hat, which represents the sample proportion. So I have a population proportion, the proportion of people at Shippensburg who graduate in 4 years. Okay, that's a number that's out there that's not necessarily easy to find unless you are in, say, the registrar's office, whoever keeps track of that. Okay, and so make believe that the registrar has that number under wraps and is not willing to let that number out. And so you have to sort of do it yourself to find, an approximation for it. And so you go around and you ask a bunch of graduates, SHIP graduates, if they did or didn't graduate in 4 years. I guess 4 or less. Okay, are people graduating on time would be my big statistical question that I've asked beforehand. Okay, and so I whittle that question down to, did you graduate in 4 or less years, or did you graduate more? I go out and I ask 50 people, and 30 of them said yes. 30 divided by 50 is my sample proportion, which I'm going to call p hat here. N is the sample size. Okay, and then now, so that gets us p hat, and that gets us n. There's only one symbol left in the thing, and that is what I'm going to call the confidence factor, the z with a subscript alpha over 2. It tells us how far to stretch our estimate in either direction. So p hat's your best guess for what p is, for a number of reasons, and so you're going to put that in the center of your guess. Okay, but then you understand that there is variability in the people that you ask. Okay? And so you have to stretch it out. You have to create that range. And so the question is, to what factor do you stretch it out? Okay? So the formula in total is p hat plus n minus, so p hat plus or minus z times that square root thing. And so that formula gets us 2 numbers, which is the lower bound and upper bound of the interval, which are the lower bound and the upper bound of the interval. And so the question is, how do we calculate that z with a subscript of alpha over 2? The subscript of alpha over 2 is there because you want area, well, you need alpha area outside and 1 minus alpha area inside. Now, also to get to the alpha, the confidence interval has a confidence level associated with it. 3 common ones are 90, 95, and 99. But technically you could have anywhere from a 0% confidence interval to a 100% confidence interval. But really, it's 1 to 99-ish. Okay, so it's a number between 0 and 100. Common ones are 90, 95, and 99. If I have a 95% confidence interval, alpha is 5%. So it's 1 minus your confidence level as a decimal. Okay? So if I want a 95% confidence interval, then alpha is 5%. Okay? 90 would mean alpha is 10, 99 would mean alpha is 1. Okay, so when I want to find out how far to stretch the interval out, I have this theoretical picture down here. 1 minus alpha, so that 1 minus alpha is your confidence level. So I want 95% to be in the middle, and I want the other 5% on the outside. Now, because 5% is on the outside, that outside means above and below. And so I have to divide it by 2 because the whole thing is symmetric. There's lots of stuff that I'm skipping here that I would take time in an actual stats class to talk about. Needless to say, alpha over 2 on the bottom in the red and alpha over 2 up top in the blue, they're going to be the same number. But I want to find the point such that alpha over 2 is there on the top and the bottom. Okay? And so when we do that, if we wanted to do that, that's where inverse CDF comes in. Okay, so that would be Q norm, and I'd plug in, if it was a 95% interval, alpha would be 0.05. And so alpha divided by 2 would be 0.025. And so that's where the first number comes in. Okay, the second number, a z is a special symbol, which means a standard normal distribution instead of a regular normal distribution. Again, things that probably don't make too much sense now, but a standard normal distribution, because it's a z, I know that it's mean 0, standard deviation 1. Okay? And I say lower dot tail is false, which means it's going to give me the upper tail. So it's going to give me the z sub alpha over 2 that I have indicated here on the graph. I don't know if you can see my mouse, my clicker. Okay, but the answer is 1.96, 1.9599, or 1.96, something you may have memorized in a stats class. Okay, anyway, here's your turn. Okay, and so this is a bit of a jump in toughness, but not so much. I want you to make your own version of d-norm. So d-norm is the density. It's the PDF. Okay, so I give you a number of hints here. There's the actual function. So this f of x, so on and so forth, that is the d-norm function. That's the density function. Okay, and so really you just want to make that. Okay, but you have to do that inside a function. So my d-norm is the function I want you to create. It has to take in 3 arguments, which is x, the mean, and the standard deviation. So x, mu, and sigma. And so you see that up there in the f, that it has 3 arguments. And so I want you to create that, and there's a check down there. If you run my d-norm of 0, 0, 1, you should get 0.3989. So again, some function arguments. Okay, so why don't you take your time, do that your turn. I'm going to stop the video again because I've talked for a while. And we'll continue on with our last bit of this stats primer.